Let alpha from I to 3 be a curve parameterized by arc length Sn. This way of describing C using S is what we call an arc length parameter for the curve.
Welcome to today's talk, Understanding Arc Length Parameterizations, with Rhino and Grasshopper. Arc length parameterizations is an essential topic in differential geometry and in multivariable calculus. So today I would like to explain the key idea behind arc length parameterizations using Grasshopper and Rhino. So arc length parameterizations and parameterized by arc length, they appear, for example, in Doccamo's book Differential Geometry of Curves and Surfaces. One of the definitions of curvatures used the phrase parameterized by arc length. Another example would be George Thomas' calculus, and he said about some words like, we call it an arc length parameter or arc length parameterization. So you can see that arc length parameterizations appear oftenly in the textbook of calculus and differential geometry. Before that, I will give you a review of vector value function and arc length. So what is vector value function? This is a very formal, rigorous definition from Thomas' calculus, and one thing I would like to highlight is the product of this equation. So as you can see, this bold symbol refers to a vector. So this one and this one and this one, they are all the coefficient of this vector value functions. So simply put, a vector value functions, its input is just one real number, and its output is three numbers. That's it. That is a vector valued function. Here is one of example of vector value functions. The input is just value from here, and it gives me back three values, and simply put 3t, meaning x equal t, y equal t, z equal t. So this is the Grasshopper version of the vector value function I just showed you. The input is 13, and x, y, z, just plug it in, is three numbers, 13. So this is the functions. It gives me back a list of three numbers, 13, 13, and 30. That's it. Just one side note, vectors and points are different concepts in mathematics, but to better understand and to easily explain, I don't have a strict definition here. Another example, a helix is called spiral curves, and the vector value function could be represented like this. The x value is cosine t, and y value is sine t, and the z value is t, and different variables can give you different kinds of shape of curves. So here is an example in Grasshopper, and I generate a list of numbers and plugging in cosine function and sine function, and also this is the normal t functions, and plug into the construct point, and it gives me back a helix spiraling up. Now let's review the arc length. So arc length, although its name starts with the arc, but it also represents the length of curve of any curve. So here's the definition of an arc length. If you forgot the calculus, don't worry. This formula is just saying that if I can subdivide the curve into many small segments and use the Pythagorean theorem, I can add them up, the length of each segment. So here is the curve. The blue one is the curve in the math world, and the red one is what I just said, subdivide the curve. So if I could subdivide the curve into the shortest length, then add them up, and it will give me almost the same length of the curve. So here's a curve in Grasshopper. The arc length is 9.9, so it's way lower than the actual length. But if I subdivide more and more and denser, the length will be almost the same. So here's the Grasshopper. So as you see, if I increase the division, the length over here will be much closer to the actual length. So the idea is that if I zoom in one subdivision, or I would say from here, at the beginning it was 2, but if I make it denser, this line, the green line here, if I make it smaller, the green line here is the y and here is the x. We are interested in the green line here. If the point get closer to here, it will be much more closer to the actual length of the red curve, the actual curve. So that's the arc length formula behind this, using the philosophy of calculus and the infinite. So to sum up, the key idea of arc length is to use the Pythagorean theorem to sum up all the subdivided curve. Then go to our core of this topic. What is arc length parameterization? From Duchamel's differential geometry, his definition of curvature involves the notion called parameterized by arc length. So what does it mean? Let's take a recap of the helix vector value function. From this equation and this picture, what do you notice? The biggest impression for me is that these equations use t as the input. So mathematically, this symbol or this equation, r means the position vector of the curve. This means a smooth curve parameterized by t. T is the input. So for arc length parameterizations and parameterized by arc length, we are saying that if we can switch the input from t to s, and that's the arc length parameterization. Then the question shifts to how could we find the relationship? I bet you have noticed. Yes, the relationship between t and s can be found by the arc length formula. Now let's use the helix function as an example, and we try to find the relationship between s and t. So this is the vector value function of helix, and the arc length equation is like this. So taking the derivative of f, g, and h, they're meaning to x, y, z respectively. So this part is x. So this part is y. So this part is z. In x, it was cosine. So the derivative of cosine is minus sine. The derivative of sine is cosine. The derivative of t is just 1. So this is how it goes from here to here. So if I sum that up, this part, cosine square plus sine square, is just 1. So this whole part is square root of 2. So taking the definite integral of this part, it just gives me square root of 2. So we now have the relationship between s and t like this. So to summarize, s is equal to square root of t, and so t equal to s over square root of 2. Now we can substitute t equal s over square root of 2 into the vector value function of helix. So if I plug t equal s over square root of 2, and this new equation is parameterized by arc length. So the whole process is called arc length parameterization. Now we wrap up all the things and verify in Grasshopper. I draw a curve, a helix like this in Grasshopper. First of all, we have to think of the domain of this curve. As you notice, the curve is ranged from 0 to 10. But I have to tell you that the domain is the domain in Rhino and Grasshopper, not the domain of mathematical space. That's been said, t greater than 0 and lower than 10 is the domain of Rhino geometry curve, not the domain of the mathematical object of the helix. So just a recap of the helix. So this is the formula of the helix function. Actually, it has a more generalized form called a cosine t and a sine t, bt. A and b are real number. Intuitively, A represents the radius of the helix if we look up from top to bottom, and B represents how the helix got pushed and or loose. This is the B value represents for. But first of all, the question is that what should be the input of T? Let's see these two trigonometry functions, cosine and sine. What would you plug into cosine and sine? Take a moment to think about it. Yes, you would plug the degree or radian into cosine and sine, right? So if I switch to this picture, what would be the domain of this curve? One idea is to take a look of the overall of the shape. As you can see, this is the start point of this helix, and it spins, and over here is the end point. As I mentioned, the input may be the degree of the radian. One idea is to count how many times this helix spin up. So there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It means that this helix rotates 10 times. So what degree and what radian each rotation? That's 2 pi, right? So the domain of T of this helix would be 10 spins, and each spin is 2 pi. So that's 20 pi. This is the domain of the helix in mathematical space. Then we can remap input value from mathematical space to Rhino space. So here is the T, and the source of the domain is 0 to 20 pi, and the target would be the domain of this Rhino curve. It ranges from 0 to 10. This value R is the result of the T after mapping to the Rhino T value. The point from the output here will be the T value using mathematical space. To sum up, using this setup, the inputs from mathematical space can evaluate a point from the curve in Rhino space. Next, we will calculate the value of A and B using this equation here. First, we will calculate the B value. The objective is to figure out the B. We have to plug Z and T here to get B. What would be an appropriate Z value of the curve and the T value of the helix function? One idea for me is to squish the helix into one line, because we only care about the height of the curve, right? I will do that. Let's break the curve out of it and move to here. So what I mean is that if I can squeeze this curve like this, and maybe in from this side, and we squeeze like this. Okay, as you can see, this curve actually can squeeze to this curve if I only care about the Z value. So we can use the endpoint to get the last point of the helix. This is the last point. So what would be the last point of the T here is what? Is you spin the 10 times of this circle, right? So T here is 20 pi. So Z is just the Z value of this point. So we set up the equation of Z and the T. Z is 10 and T is 20 pi. After some calculation, B is equal to 1 over 2 pi. Next, we will figure out what is A. Our objective is to figure out the X value represented by A cosine T and Y value represented by A sine T. I can just pick some random number and just a random T and figure out the X value and Y value of the point. I would say 3.3. This is the T over here. So A cosine 3.3 and A sine 3.3. So this is the mathematical space. So I remap to the Rhino domain 0 to 10. So this point will be this one. So I can deconstruct my point from here, and the value of X and Y is what I'm interested in. So that would be minus 0.98746 8. The y value would be minus 0.157744. So that's the setup of the t and the x and y. We can solve this equation using the trigonometry function. There will be squared both sides and add them up. So this part will be 1 using the equation that sine squared plus cosine squared is equal to 1. To wrap up, our helix function would be like this: a equal to 1, so there's nothing here, and a equal to 1, nothing here as well. And the b is that 1 over 2 pi. So this is the helix function. We can use the cosine and sine components and also the 1 over 2 pi equation here to represent the curve from our mathematical space. As you can see, the point from Rhino and the point from our mathematical expression, the error is quite small, which means our equation is correct. Next, we will reparameterize from T to arc length S. So the objective is figure out what would be the equation using S as the parameter from this equation to this equation. Again, we will use the arc length formula to calculate this. So there is nothing new here. It's just this is the same as cosine. This will be sine, and this will be 1 over 2 pi t, and the derivative is this guy. So sum them up, and we got this a little bit ugly but acceptable relationship between S. So this is the relationship between S and T. So we can organize a little bit, even uglier, but I can accept. Luckily, we find using S to represent T. Now we can plug S into T. So this will be a little bit overwhelming, but it's true. This part is T, and this part is also T, and this part is also T. So changing T from S would be like this. So we got X and Y and Z and everything from this guy. So we have the equation of X, Y, Z. We can also plug everything into Grasshopper. So this one is the ugly component, and the other is just similar, and this is represent X, and this represent Y, and this represents Z, and this whole part the mathematical space in Rhino, and this part is Rhino. This function is S. Okay, now we are back to Rhino and Grasshopper, and let's plug this equation into Grasshopper. So first of all, let me set up the inputs as number, and let me call it X. So this will be the input of this one, S. And let me create an equation or expression, and I have inputs from here. And I just want to use this equation to represent this ugly part of this one. This ugly part. So that would be 1 over something. And what's something? Something would be square root. And what's inside the square root? There is 1. And there is also, something over something. And what's under something? There will be 4 multiple pi square. Okay, now we finished this ugly part, and let me just also list out the x, y, z value. So this x, there will be y, there will be also z. Okay, and for the z part, I also need something, a real number, and that will be 1 over 2 pi. So there will be 1 over something, there will be 2 pi, and that's it. And so here is the multiplication relationship. So I would use this component, and 1 over 2 pi, and this ugly part, and I can add one more input and plug the x input here, and that will be our z. And next part should be the y and sine function. and I can use s multiply, use this ugly function, no, ugly value to multiply the s and plug in to sine. So this is our y. And for cosine part, they're much similar. And let me put cosine function here. And there is also need one multiple. Let me plug this part and s part. So plug this guy into here. And this one will be x. Okay, let me just quickly summarize a little bit. So this guy, yellow, is this ugly function, and s is this one. So s multiply this ugly one, and this will be this one, and plug the whole part into cosine function. So after this, the x is this. So for y and z, that will be pretty much the same. Now go to the arc length part, and for simplicity, I will use evaluate length, and this one. Let me see how long of this curve, and it's saying that it will be 63.62235. So let's copy this data and slider, using number slider, and to change the maximum value, that's the maximum length of this curve, hit OK. So this would be our input s. So this is the arc length, and the total value match the arc length of this curve. So I plug in here. This is the input. I can also plug in here. But notice that this is length factor for curve evaluation. So I will need to divide it. So here's my input, and this is my arc length. So there will be some factor, maybe like 0.59, and plug it into here. So this is our point. Okay. The idea is that this point evaluate from here is the one we evaluate from here. Let's take a look. Let's use construct point, plug x, y, and z here, and use the distance function to evaluate the error. Okay, that will be pretty much the same. Is that 0.000248? Okay, that's quite good. Why is not good as the previous arc length? Because as you notice, there's lots of square roots operation here. So that would be one drawback of this one. And if you're interested, you can take a course of numerical analysis. But the whole idea here is that we can change the parameter from t to s to reparameterize the curve using the arc length. And this is purely from mathematical. So to sum up, this part is the mathematical setup from our equation and our calculation and reparameterized by arc length. And this part is derived in Rhino. So as you can see, our result is pretty good. So to summarize, the following example use t as the parameter, this one. And the next example use the arc length s as the parameter. So this equation is called parameterized by arc length s. So changing from this equation to this equation is called arc length parameterization. So that's all for today. Thanks for watching. I hope it helps. Thank you.